What if everything you thought you knew about the universe was just the tip of the iceberg? Imagine staring into the night sky, only to realize that some of the most bizarre and unexplained phenomena are lurking out there, defying the laws of physics as we know them. From mysterious signals that could be messages from distant civilizations to invisible forces shaping the cosmos, space is filled with anomalies that challenge our very understanding of reality. Today, we're diving into 25 of the most mind-bending space mysteries that will make you question everything you thought you knew about the universe. These aren't just curiosities, they're cosmic puzzles that even the brightest minds on Earth are struggling to solve. So, buckle up and get ready to explore the strange, the unexplained, and the downright eerie as we uncover the secrets of the cosmos that will leave you in awe and wonder. Let's begin. Now turning to the first anomaly on our list, we encounter one of the most tantalizing mysteries in the history of space exploration, the WOW signal. Detected on August 15, 1977, this powerful radio signal was picked up by the Big Ear radio telescope at Ohio State University. Lasting for 72 seconds, the signal was so unusual and intense that astronomer Jerry Amon famously circled it on the printout and wrote, "Wow," next to it, giving the phenomenon its iconic name. What made this signal so extraordinary was its frequency of 1,420 MHz, a range that is typically free from interference and often considered a potential band for interstellar communication. The signal appeared to originate from the direction of the constellation Sagittarius, but despite numerous attempts to detect it again, it has never been observed since. This one-time burst has fueled endless speculation, with theories ranging from natural cosmic phenomena to the possibility of an intentional transmission from an extraterrestrial civilization. Scientists have proposed explanations such as a passing comet or a distant star emitting a rare burst of energy, but none have been able to fully account for the signal's unique characteristics. The WOW signal remains a profound enigma, a fleeting whisper from the cosmos that continues to challenge our understanding of what might be out there. Could it have been a message from an advanced alien race or simply a cosmic coincidence? The truth remains hidden, leaving us to wonder and imagine the possibilities. Now turning to the second anomaly on our list, we delve into one of the most perplexing mysteries of the cosmos, dark matter. This invisible substance is believed to make up approximately 85% of the universe's total mass, yet it remains completely undetectable by conventional means. The story of dark matter begins in the 1930s, when Swiss astronomer Fritz Zwicky observed that galaxies within the Coma cluster were moving far faster than their visible mass could account for. He proposed the existence of unseen matter, or dark matter, to explain this discrepancy. Decades later, American astronomer Vera Rubin provided further evidence by studying the rotation curves of galaxies, which showed that stars on the outer edges were moving at speeds that defied the laws of gravity based on visible matter alone. Dark matter's role in the universe is monumental. It acts as the cosmic scaffolding, holding galaxies together and shaping the large-scale structure of the universe. Without it, galaxies would fly apart, and the universe as we know it would not exist. Yet, despite its overwhelming presence, dark matter does not interact with light or any form of electromagnetic radiation, making it invisible to telescopes. Scientists have devised ingenious methods to infer its existence, such as observing the gravitational lensing effect, where the gravity of dark matter bends the light from distant objects. However, directly detecting dark matter has proven to be an immense challenge. Numerous experiments, such as those using underground detectors and particle colliders, have been conducted to capture even the faintest hint of dark matter particles. Theories suggest that dark matter could be composed of weakly interacting massive particles, or WIMP, but so far, none have been conclusively identified. The search continues as understanding dark matter could unlock the secrets of the universe's composition and evolution. Why does this elusive substance dominate the cosmos, yet remain so hidden from our senses? The answer lies somewhere in the vast, dark expanse of the universe, waiting to be discovered. Now turning to the third anomaly on our list, we encounter a force even more enigmatic than dark matter, dark energy. This mysterious entity is responsible for the accelerated expansion of the universe, a discovery that has fundamentally reshaped our understanding of the cosmos. The story of dark energy begins in the late 1990s, when two independent teams of astronomers were studying distant supernova to measure the rate of the universe's expansion. To their astonishment, they found that the universe was not only expanding but doing so at an ever-increasing speed. This revelation was so unexpected that it earned the researchers the Nobel Prize in Physics in 2011. Dark energy is believed to make up approximately 68% of the universe's total energy content, dwarfing both dark matter and ordinary matter. Yet, unlike dark matter, which exerts a gravitational pull, dark energy appears to act as a repulsive force, pushing galaxies apart at an accelerating rate. This behavior defies the predictions of classical physics, which would expect the expansion of the universe to slow down over time due to gravity. Instead, dark energy seems to dominate, driving the cosmos toward an uncertain future. The implications of dark energy are profound. If its influence continues to grow, it could lead to a big freeze, where the universe expands so rapidly that galaxies, stars, and even atoms are torn apart. Alternatively, some theories suggest that dark energy could evolve over time, potentially leading to a Big Rip scenario where the fabric of spacetime itself is shredded. These possibilities challenge our understanding of the fundamental laws of physics and raise questions about the ultimate fate of the universe. Despite its significance, dark energy remains one of the greatest mysteries in science. Its nature is unknown, and it does not interact with light or matter in any detectable way. Scientists have proposed various theories to explain it, including the possibility that it is a property of space itself, known as the cosmological constant, or that it arises from a new, undiscovered field of physics. Yet, no definitive answers have been found. The search for dark energy continues with projects like the Dark Energy Survey and the upcoming Euclid Space Telescope aiming to map its effects on the universe's large-scale structure. Understanding dark energy could not only reveal the fate of the cosmos, but also provide insights into the very fabric of reality. Why does this mysterious force dominate the universe, and what does it mean for the future of everything we know? The answers lie hidden in the vast, expanding expanse of space, waiting to be uncovered. Now turning to the fourth anomaly on our list, we delve into one of the most perplexing questions in science, the Fermi Paradox. Named after the physicist Enrico Fermi, this paradox highlights the stark contradiction between the high probability of extraterrestrial life existing in the universe and the complete lack of evidence for it. With billions of galaxies, each containing billions of stars and planets, the odds seem overwhelmingly in favor of life emerging elsewhere. Yet, despite decades of searching, we have found no definitive signs of intelligent civilizations beyond Earth. The Fermi Paradox forces us to confront a troubling question. Where is everyone? One possible explanation is the concept of the Great Filter, a hypothetical barrier that prevents life from advancing to a stage where it can communicate across interstellar distances. This filter could occur at any point in the evolutionary timeline, from the emergence of simple life forms to the development of advanced civilizations. If the Great Filter lies in our past, it means that the emergence of intelligent life is extraordinarily rare, and we might be among the few, if not the only, intelligent species in the universe. However, if the Great Filter lies ahead of us, it suggests that advanced civilizations inevitably face a catastrophic event that prevents their survival, such as self-destruction through war or environmental collapse. Another explanation for the Fermi paradox is the sheer rarity of intelligent life. Even if life is common in the universe, the conditions required for the development of complex, intelligent beings might be exceedingly rare. Factors such as the stability of a planet's climate, the presence of a large moon to stabilize its rotation, and the absence of frequent extinction-level events could all play a role in determining whether life evolves beyond simple organisms. Additionally, the vast distances between stars and the limitations of technology might make interstellar communication or travel nearly impossible, even for advanced civilizations. Some scientists have proposed that extraterrestrial civilizations might exist but choose to remain hidden, either out of caution or because they have evolved beyond the need for physical communication. Others suggest that we might simply be looking in the wrong places or using the wrong methods to detect signs of life. The search for extraterrestrial intelligence, or SETI, continues to explore these possibilities, using advanced telescopes and innovative techniques to scan the cosmos for signals or other evidence of alien life. The Fermi paradox challenges us to rethink our assumptions about life, intelligence, and our place in the universe. Are we alone, or are there others out there waiting to be discovered? As we continue to explore the cosmos, this paradox reminds us of the profound mysteries that still await us, urging us to keep searching for answers in the vast, uncharted expanse of space. Now turning to the fifth anomaly on our list, we encounter one of the most enigmatic forces in the cosmos, the Great Attractor. This mysterious gravitational anomaly, located in the direction of the constellations Centaurus and Hydra, exerts an immense pull on galaxies, including our own Milky Way. Despite its profound influence, the Great Attractor remains shrouded in mystery, largely because it lies behind the dense plane of our galaxy, making it incredibly difficult to observe directly. The Great Attractor was first discovered in the 1970s when astronomers noticed that galaxies in our local region of the universe were moving toward a specific point at an unusually high speed. This motion defied the expected expansion of the universe, suggesting the presence of a massive gravitational force at work. Estimates suggest that the Great Attractor has a mass equivalent to tens of thousands of Milky Way galaxies, yet its exact nature and composition remain unclear. One of the biggest challenges in studying the Great Attractor is its location. It sits in what astronomers call the zone of avoidance, an area of the sky obscured by the dense dust and stars of the Milky Way's galactic plane. This makes it nearly impossible to observe using visible light telescopes. However, advancements in technology, such as infrared and radio telescopes, have allowed scientists to peer through this cosmic veil, revealing glimpses of the structures hidden behind it. What we do know is that the Great Attractor is not a single object, but rather a concentration of mass, likely a massive cluster of galaxies or a supercluster. Some theories suggest it could be part of an even larger structure, such as the Laniakea supercluster, which encompasses our galaxy and thousands of others. The gravitational pull of the Great Attractor is so strong that it influences the motion of galaxies across hundreds of millions of light years, shaping the large-scale structure of the universe. The implications of the Great Attractor are profound. It challenges our understanding of cosmic forces and the distribution of matter in the universe. By studying this anomaly, scientists hope to gain insights into dark matter, the invisible substance that makes up most of the universe's mass, and dark energy, the mysterious force driving the accelerated expansion of the cosmos. The Great Attractor also raises questions about the ultimate fate of our galaxy and the universe as a whole. Will the Milky Way eventually be drawn into this colossal structure, or will the expansion of the universe prevent such a collision? As we continue to explore the Great Attractor, it serves as a reminder of how much we still have to learn about the universe. This gravitational enigma not only pulls galaxies toward it, but also pulls us deeper into the mysteries of the cosmos, urging us to uncover the secrets hidden within its immense gravitational embrace. Now turning to the sixth anomaly on our list, we encounter a star that has baffled astronomers and sparked endless speculation. Tabby Star, also known as KSE 8462852. Located approximately 1,400 light-years away in the constellation Cygnus, this star has become famous for its bizarre and unpredictable dimming patterns which defy conventional explanations. The mystery of Tabby Star began in 2015 when astronomers noticed something unusual in the data from the Kepler Space Telescope. Unlike most stars, which dim in a regular, predictable manner when planets pass in front of them, Tabby Star exhibited erratic and dramatic drops in brightness. These dips were not only irregular but also far more significant than anything caused by a typical planet. At times, the star's brightness dropped by as much as 22%, a phenomenon that left scientists scratching their heads. One of the most intriguing theories proposed to explain these strange dimming patterns involves the idea of alien megastructures. Some scientists speculated that the dips in brightness could be caused by a massive artificial structure, such as a Dyson sphere, built by an advanced extraterrestrial civilization to harness the star's energy. While this idea captured the public's imagination, it remains highly speculative, and most astronomers lean toward more natural explanations. One such explanation involves the presence of vast clouds of dust and debris orbiting the star. These clouds could periodically block its light, causing the observed dimming. Another possibility is that Tabby Star is surrounded by a swarm of comets or fragments from a shattered planet, which could create irregular patterns of light blockage. However, even these natural explanations struggle to fully account for the star's extreme and unpredictable behavior. Adding to the mystery, Tabby Star has also shown long-term dimming over the past century. Historical data reveals that the star has gradually become fainter, a trend that is difficult to reconcile with any known stellar processes. This has led some researchers to suggest that the star itself might be undergoing unusual changes, such as internal instabilities or interactions with a nearby companion star. Despite years of observation and analysis, Tabby Star remains an enigma. It challenges our understanding of stellar behavior and forces us to consider possibilities that stretch the boundaries of science. Whether the answer lies in natural phenomena or something more extraordinary, Tabby Star continues to captivate astronomers and the public alike, reminding us that the universe is full of surprises waiting to be uncovered. As we move forward, this cosmic puzzle invites us to keep exploring, questioning, and imagining the possibilities that lie beyond our current knowledge. Now turning to the seventh anomaly on our list, we delve into the enigmatic phenomenon of fast radio bursts, or FRB. These are incredibly brief but intensely powerful bursts of radio waves that originate from deep space, lasting only a few milliseconds. Despite their fleeting nature, they release as much energy in that short time as the sun does in an entire day. First discovered in 2007, FRBs have since become one of the most puzzling mysteries in modern astronomy. The origins of these bursts remain largely unknown, though several theories have been proposed. One leading explanation points to neutron stars, particularly those with extremely strong magnetic fields known as magnetars. These dense, rapidly spinning remnants of supernova explosions could produce the immense energy required for FRBs. In fact, in 2020, astronomers detected an FRB originating from a magnetar within our own galaxy, providing the first direct evidence linking these bursts to such objects. However, not all FRBs fit this explanation, leaving room for other possibilities. Another intriguing theory suggests that FRBs could be signals from advanced extraterrestrial civilizations. While this idea is speculative, it captures the imagination, as these bursts could potentially be a form of interstellar communication or even the byproduct of alien technology. However, most scientists lean toward natural explanations, given the vast distances and energies involved. Adding to the mystery, some FRBs are one-time events, while others repeat at irregular intervals. The repeating bursts, in particular, challenge our understanding as they imply a source that can produce these intense emissions multiple times without being destroyed. This has led to further speculation about exotic cosmic phenomena, such as collisions between neutron stars or interactions with black holes. Despite significant advancements in detection technology, FRBs remain elusive and difficult to study. Their unpredictable nature and the vast distances they travel make it challenging to pinpoint their exact sources. Yet, each new detection brings us closer to unraveling their secrets, offering tantalizing clues about the extreme environments and processes that shape our universe. Fast radio bursts remind us that even the briefest signals from the cosmos can hold profound mysteries. As we continue to explore these fleeting yet powerful bursts, we are reminded of how much we still have to learn about the universe and the extraordinary phenomena it contains. With each discovery, we inch closer to understanding the forces that govern the cosmos, and perhaps to uncovering answers that could reshape our understanding of reality itself. Now turning to the 8th anomaly on our list, we explore the perplexing case of the Pioneer Anomaly. This mystery revolves around the unexpected deceleration of the Pioneer 10 and Pioneer 11 spacecraft as they traveled through the outer reaches of our solar system. Launched in the early 1970s, these spacecraft were designed to study Jupiter, Saturn, and beyond, but their journey took an unexpected turn when scientists noticed something strange. As the Pioneers ventured farther from the Sun, their trajectories began to deviate slightly from what was predicted by Newtonian physics and Einstein's theory of general relativity. Both spacecraft were slowing down more than expected, as if an unseen force was gently tugging them back toward the Sun. This tiny but consistent deceleration, measured at about 8.74 times 10 to the power of -10 meters per second squared, became known as the Pioneer Anomaly. For decades, this anomaly puzzled scientists, sparking a range of theories to explain it. One of the leading explanations points to thermal radiation. The spacecraft were powered by radioisotope thermoelectric generators, which produced heat as a byproduct. It's possible that this heat, radiating unevenly from the spacecraft, created a tiny but measurable thrust in the opposite direction of their motion, effectively slowing them down. This theory gained traction after detailed thermal models of the spacecraft were developed, showing that such an effect could account for much of the observed deceleration. However, not everyone was convinced. Some researchers proposed that the Pioneer Anomaly might hint at new physics, suggesting that our understanding of gravity or the behavior of objects in deep space might be incomplete. Could there be an unknown force at play, or perhaps a subtle flaw in our current theories of gravity? These questions fueled speculation and debate, making the Pioneer Anomaly a focal point for those exploring the boundaries of our knowledge. In the end, further analysis and advancements in spacecraft design helped shed light on the mystery. By studying the thermal properties of more recent missions, such as the New Horizons probe, scientists were able to refine their understanding of how heat radiation affects spacecraft trajectories. While the thermal explanation now seems to account for most of the Pioneer Anomaly, the case remains a fascinating reminder of how even the smallest discrepancies can lead to big questions about the universe. The Pioneer Anomaly serves as a testament to the precision of modern science and the enduring curiosity that drives us to explore the unknown. It reminds us that even in the vast emptiness of space, there are still mysteries waiting to be uncovered, and that every anomaly, no matter how small, has the potential to challenge our understanding of the cosmos. Now turning to the 9th anomaly on our list, we encounter the enigmatic Oumuamua, the first known interstellar object to pass through our solar system. Discovered in October 2017 by the Pan-STARRS telescope in Hawaii, Oumuamua immediately captured the attention of astronomers and the public alike. Its name, meaning scout or messenger from afar in Hawaiian, perfectly encapsulates its mysterious nature. What made Oumuamua so extraordinary was its unusual shape and behavior. Unlike typical asteroids or comets, Oumuamua appeared to be highly elongated, resembling a cigar or a pancake, with estimates suggesting it was about 10 times longer than it was wide. This bizarre shape was unlike anything observed in our solar system, sparking intense curiosity about its origins and composition. Adding to the intrigue was Oumuamua's motion. As it traveled through our solar system, it exhibited a slight but unexpected acceleration that couldn't be fully explained by gravity alone. This led to speculation about what might be propelling it. Some scientists suggested that outgassing, a process where comets release gas as they heat up, could be responsible. However, no visible coma or tail, typical of comets, was detected around Oumuamua, leaving this explanation incomplete. The lack of clear outgassing evidence fueled even more exotic theories. Some researchers proposed that Oumuamua might be a fragment of a larger object, perhaps shattered by a collision in its home system. Others speculated that it could be a piece of a rogue planet or even an artificial object, such as a solar sail from an advanced extraterrestrial civilization. While these ideas remain speculative, they highlight the profound mystery surrounding this interstellar visitor. Despite the debates, one thing is certain: Oumuamua has opened a new chapter in our understanding of the cosmos. Its brief visit challenged our assumptions about the nature of interstellar objects and reminded us that the universe is full of surprises. As we continue to study the data gathered during its passage, Oumuamua serves as a tantalizing glimpse into the vast, uncharted realms beyond our solar system, leaving us with more questions than answers about what else might be out there. Now turning to the 10th anomaly on our list, we delve into one of the most perplexing puzzles in modern physics, the black hole information paradox. This mystery lies at the heart of a fundamental conflict between two of the most successful theories in science, quantum mechanics and general relativity. At its core, the paradox questions whether information that falls into a black hole is lost forever, challenging our understanding of the universe's most basic principles. According to general relativity, black holes are regions of space-time where gravity is so intense that nothing, not even light, can escape. Once matter or energy crosses the event horizon, the boundary of a black hole, it is thought to be irretrievably lost to the outside universe. However, quantum mechanics, which governs the behavior of particles at the smallest scales, tells us that information cannot be destroyed. This creates a direct contradiction. If information is preserved, as quantum mechanics insists, where does it go when it enters a black hole? The paradox was brought into sharp focus by the work of physicist Stephen Hawking, who discovered that black holes are not entirely black. Through a process now known as Hawking radiation, black holes can emit energy and slowly lose mass over time. This radiation is thought to be purely thermal, meaning it carries no information about the matter that originally fell into the black hole. If a black hole eventually evaporates completely through this process, it would seem that all the information about the objects it consumed is lost forever, violating the principles of quantum mechanics. This dilemma has led to a flurry of theoretical work aimed at resolving the paradox. One prominent idea is the holographic principle, which suggests that all the information about the matter swallowed by a black hole is encoded on its event horizon, much like a hologram. Another theory proposes that information might escape through quantum tunneling or be preserved in the remnants of an evaporated black hole. Some even speculate that black holes might not be the ultimate endpoints of information, but rather gateways to other regions of spacetime. Despite decades of research, the black hole information paradox remains unresolved, standing as one of the greatest challenges in theoretical physics. It forces us to confront the limitations of our current understanding and pushes scientists to explore new frameworks that might reconcile quantum mechanics and general relativity. As we continue to probe this mystery, the paradox serves as a reminder of how much we still have to learn about the nature of reality itself. Now turning to the 11th anomaly on our list, we encounter a cosmic mystery that has left scientists scratching their heads, the axis of evil. This peculiar term refers to an unexpected alignment in the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates the entire universe. Discovered in the early 2000s, this alignment challenges some of our most fundamental assumptions about the universe's structure and origins. The cosmic microwave background, or CMB, is a snapshot of the universe when it was just 380,000 years old. It provides a wealth of information about the early universe, including its temperature fluctuations and density variations. These fluctuations are expected to be random, reflecting the chaotic conditions of the Big Bang. However, when scientists analyzed the data, they found something startling. Certain patterns in the CMB appeared to align along a specific axis, as if the universe had a preferred direction. This alignment, dubbed the axis of evil, defies the cosmological principle, which states that the universe should look the same in all directions on large scales. The implications of this discovery are profound. If the universe has a preferred direction, it could mean that our understanding of the Big Bang is incomplete, or that there are forces at play we have yet to uncover. Some theories suggest that the alignment might be evidence of a multiverse, where our universe is just one of many, each with its own unique properties. Others propose that it could be a sign of new physics, such as modifications to Einstein's theory of general relativity or the influence of dark energy on the early universe. Despite extensive research, the axis of evil remains a mystery. Some scientists argue that the alignment could be a statistical fluke or an artifact of the way the data is analyzed. However, the persistence of the anomaly in multiple datasets suggests that there might be more to it. As we continue to study the CMB with increasingly precise instruments, the axis of evil serves as a reminder that the universe still holds many secrets waiting to be uncovered. This anomaly not only challenges our understanding of the Big Bang, but also invites us to rethink the very nature of reality itself. Now turning to the 12th anomaly on our list, we venture into one of the most puzzling regions of the cosmos, the Boötes void. This vast, nearly empty expanse of space, located in the constellation of Boötes, is one of the largest known voids in the universe, spanning an astonishing 330 million light-years across. The Boötes void is so enormous that it challenges our understanding of how galaxies and cosmic structures form. Unlike most regions of the universe, which are teeming with galaxies, the Boötes void is eerily sparse. While the average region of space contains thousands of galaxies, this void holds only a few dozen. This extreme emptiness raises questions about the processes that govern galaxy formation and the distribution of matter in the universe. How could such a vast region remain so empty? And what does it tell us about the large-scale structure of the cosmos? One leading theory suggests that the Boötes void formed as a result of the universe's expansion. In the early universe, small fluctuations in density led to the clumping of matter, creating the cosmic web of filaments and voids we see today. The Boötes void may simply be an unusually large and empty region within this web. However, its sheer size and emptiness still defy expectations, prompting scientists to consider alternative explanations. Some speculate that the void could be the result of interactions between dark energy and dark matter, the mysterious forces that shape the universe's evolution. The implications of the Boötes void extend beyond its emptiness. Its existence challenges the cosmological principle, which assumes that the universe is homogeneous and isotropic on large scales. If voids like Boötes are more common than we think, it could mean that the universe's structure is far more complex and varied than our current models suggest. This anomaly also raises questions about the fate of galaxies within such voids. Do they evolve differently than galaxies in denser regions? And what does this mean for the overall evolution of the universe? As we continue to explore the cosmos, the Boötes void serves as a stark reminder of how much we still have to learn. Its vast emptiness is not just a curiosity, but a window into the fundamental processes that shape the universe. By studying this anomaly, we may uncover new insights into the nature of dark energy, the distribution of matter, and the ultimate fate of the cosmos. The Boötes void challenges us to rethink our assumptions and pushes the boundaries of our understanding, proving once again that the universe is full of surprises. Now turning to the 13th anomaly on our list, we shift our focus closer to home, to Earth's closest celestial neighbor, the Moon. While the Moon may seem familiar, it holds a mystery that has puzzled scientists for decades: its ancient magnetic field. Unlike Earth, which has a strong and active magnetic field generated by its molten core, the Moon today is magnetically quiet. But evidence from lunar rocks suggests that billions of years ago, the Moon once had a magnetic field as strong as Earth. So what happened to it, and how did it form in the first place? Theories about the Moon's magnetic field point to its early history. Around 4 billion years ago, the Moon was much closer to Earth, and its interior was hotter. Some scientists believe that the Moon's magnetic field was generated by a dynamo effect, similar to Earth's, where the movement of molten iron in the core created a magnetic field. However, as the Moon cooled and its core solidified, this dynamo effect ceased, causing the magnetic field to fade away. But this explanation raises another question. How did the Moon's core remain molten long enough to sustain a magnetic field for hundreds of millions of years? One intriguing theory suggests that the Moon's magnetic field was powered by a different mechanism altogether. During its early history, the Moon may have experienced intense tidal forces from Earth, which caused friction and heating in its interior. This tidal heating could have kept the core molten and generated the magnetic field. Another possibility is that massive impacts during the Moon's formation stirred up its interior, creating temporary conditions for a magnetic dynamo. These impacts could have also brought in materials that contributed to the Moon's magnetic properties. The disappearance of the Moon's magnetic field also has implications for its surface. Without a magnetic shield, the Moon has been exposed to the full force of solar radiation and cosmic rays for billions of years. This exposure has shaped the Moon's surface, creating the barren, cratered landscape we see today. It also raises questions about the potential for life on other moons or planets without magnetic fields. Could they sustain life, or would they be as inhospitable as our Moon? The Moon's magnetic field is a reminder that even the most familiar objects in our solar system hold secrets waiting to be uncovered. By studying this anomaly, scientists hope to learn more about the Moon's formation, its relationship with Earth, and the processes that shape planetary magnetic fields. As we continue to explore the Moon, both through robotic missions and future human expeditions, we may uncover new clues that shed light on this ancient mystery. The Moon's magnetic field may be gone, but its story continues to captivate and challenge our understanding of the cosmos. Now turning to the 14th anomaly on our list, we delve into a cosmic puzzle that has left astronomers scratching their heads: the Hubble tension. This mystery revolves around a discrepancy in how fast the universe is expanding, a fundamental measurement that shapes our understanding of the cosmos. The Hubble tension arises from two different methods of measuring the universe's expansion rate, and they don't agree. One method uses the cosmic microwave background, the faint afterglow of the Big Bang, while the other relies on observations of nearby stars and galaxies. Both approaches are precise, yet they give conflicting results. So, what's going on? The first method, based on the cosmic microwave background, suggests that the universe is expanding at a certain rate. This measurement comes from the Planck satellite, which has mapped the early universe in incredible detail. The second method, using nearby objects like Cepheid variable stars and supernova, suggests a faster expansion rate. This discrepancy isn't just a small error. It's a significant difference that challenges our understanding of the universe's evolution. If both methods are correct, then there's something fundamental we're missing about how the universe works. One possible explanation for the Hubble tension involves dark energy, the mysterious force driving the universe's accelerated expansion. Dark energy makes up about 70% of the universe's energy content, but we still don't fully understand its nature. Some scientists suggest that dark energy might be changing over time, becoming stronger or weaker, which could explain the differing expansion rates. Others propose that there might be unknown particles or forces at play, altering the way the universe expands. These ideas push the boundaries of our current physics, hinting at new discoveries waiting to be made. Another intriguing possibility is that our measurements are being affected by something we haven't accounted for, like local variations in the density of matter or errors in our observational techniques. For example, the region of space we're using to measure the expansion rate might not be representative of the universe as a whole. Alternatively, there could be systematic errors in how we interpret the data from distant supernova or Cepheid stars. These uncertainties highlight the complexity of cosmology and the challenges of studying a universe that's constantly changing. The Hubble tension isn't just a technical problem. It has profound implications for our understanding of the universe's fate. If the expansion rate is faster than we thought, it could mean that dark energy is more powerful than we realized, potentially leading to a Big Rip scenario where the universe tears itself apart. On the other hand, if the discrepancy is resolved in favor of the slower rate, it could mean that our models of dark energy need to be revised. Either way, solving the Hubble tension could revolutionize our understanding of the cosmos. As astronomers continue to refine their measurements and develop new techniques, the Hubble tension remains one of the most exciting challenges in modern cosmology. It's a reminder that even the most fundamental aspects of the universe are still up for debate. By unraveling this mystery, we may uncover new insights into dark energy, the nature of space and time, and the ultimate fate of the cosmos. The Hubble tension isn't just a problem, it's an opportunity to push the boundaries of human knowledge and explore the deepest secrets of the universe. Now turning to the 15th anomaly on our list, we explore a mysterious glow emanating from the heart of our galaxy, the galactic center excess. This phenomenon refers to an unexpected surge of gamma-ray radiation coming from the center of the Milky Way, a region densely packed with stars, black holes, and other cosmic wonders. While some gamma rays are expected from these sources, the amount detected is far greater than what current models can explain. So, what's causing this excess? Scientists have proposed several intriguing theories, each with its own implications for our understanding of the universe. One leading explanation involves dark matter, the elusive substance that makes up about 85% of the universe's mass. According to this theory, dark matter particles could be colliding and annihilating each other in the galactic center, producing gamma rays as a byproduct. If true, this would be a groundbreaking discovery, offering the first direct evidence of dark matter's existence. However, proving this theory is no easy task. Dark matter doesn't interact with light or ordinary matter, making it incredibly difficult to detect. The gamma-ray excess could be our best clue yet, but it's still a puzzle waiting to be solved. Another possibility is that the excess gamma rays are coming from pulsars, highly magnetized neutron stars that spin rapidly and emit beams of radiation. These cosmic lighthouses are known to produce gamma rays, and the galactic center is home to thousands of them. Some scientists argue that a population of faint, previously undetected pulsars could be responsible for the excess. While this explanation doesn't involve dark matter, it would still provide valuable insights into the behavior of these fascinating objects and the environment at the heart of our galaxy. There's also the chance that the excess is caused by a combination of factors, including both dark matter and pulsars. For example, some gamma rays might come from dark matter annihilation, while others are produced by pulsars. Alternatively, there could be entirely new astrophysical processes at work that we haven't yet discovered. The galactic center is an incredibly complex and dynamic region, and untangling its mysteries requires careful observation and innovative thinking. The galactic center excess isn't just a scientific curiosity. It has profound implications for our understanding of the universe. If dark matter is indeed the source, it could open the door to a new era of particle physics, revealing the nature of one of the universe's greatest mysteries. On the other hand, if pulsars or other known objects are responsible, it would deepen our knowledge of the galactic center and the processes that shape it. Either way, solving this anomaly could reshape our understanding of the cosmos. As astronomers continue to study the galactic center with increasingly powerful telescopes and instruments, the mystery of the gamma-ray excess remains a tantalizing challenge. It's a reminder that even in our own backyard, the universe is full of surprises. By unraveling this enigma, we may uncover new insights into dark matter, pulsars, and the forces that govern the cosmos. The galactic center excess isn't just a puzzle, it's a window into the hidden workings of the universe, waiting to be opened. Now turning to the 16th anomaly on our list, we delve into the vast and intricate structure of the universe known as the cosmic web. Imagine the universe not as a random scattering of galaxies, but as an enormous, interconnected network of filaments and voids stretching across billions of light years. This cosmic tapestry is the large-scale structure of the universe, and it holds the key to understanding how everything we see today came to be. The cosmic web is made up of long, thread-like filaments of dark matter and gas, with galaxies clustered along these filaments like beads on a string. Between these filaments lie vast, empty regions called voids, where matter is sparse and galaxies are few and far between. This structure emerged from the tiny fluctuations in density that existed in the early universe, amplified over billions of years by the force of gravity. As matter clumped together, it formed the dense filaments, while the regions with less matter expanded into the voids we see today. But the cosmic web isn't just a static structure, it's a dynamic, evolving network. Galaxies are constantly moving along the filaments, pulled by gravity toward the densest regions where they collide and merge. This process shapes the growth of galaxies and the distribution of matter throughout the universe. Yet, despite its importance, the cosmic web challenges our understanding of cosmic evolution in profound ways. One of the biggest mysteries is the role of dark energy, the mysterious force driving the accelerated expansion of the universe. As the universe expands, the filaments of the cosmic web are stretched and the voids grow larger. This raises questions about how the web will evolve in the future. Will the filaments eventually thin out and break apart, or will dark energy's influence lead to an entirely new cosmic structure? Scientists are still grappling with these questions, using simulations and observations to piece together the story of the cosmic web. Another challenge is mapping the web itself. Because much of it is made up of dark matter which doesn't emit light, we can't see it directly. Instead, astronomers rely on indirect methods, such as observing the distribution of galaxies or using gravitational lensing to trace the invisible dark matter. These techniques have revealed a stunningly complex and beautiful structure, but they also highlight how much we still have to learn. The cosmic web isn't just a scientific curiosity, it's a fundamental part of the universe's architecture. By studying it, we gain insights into the origins of galaxies, the nature of dark matter and dark energy, and the forces that have shaped the cosmos over billions of years. It's a reminder that the universe is far more interconnected and intricate than we often imagine, and that every thread in this cosmic tapestry tells a story about the history and future of everything we know. Now turning to the 17th anomaly on our list, we encounter one of the most puzzling mysteries in modern cosmology, the missing baryon problem. When scientists calculate the total amount of ordinary matter, or baryonic matter, that should exist in the universe based on the Big Bang theory, they find a significant discrepancy. A large portion of this matter seems to be missing, and its whereabouts remain one of the greatest unsolved questions in astrophysics. Ordinary matter, the stuff that makes up stars, planets, and even us, is just a small fraction of the universe's total content. The rest is dominated by dark matter and dark energy, but even within that small fraction, something doesn't add up. Observations of the early universe, such as those from the cosmic microwave background, suggest that baryonic matter should account for about 5% of the universe's total mass energy. Yet, when astronomers tally up all the visible matter in galaxies, stars, and gas clouds, they only find about half of what's expected. So, where is the rest? One leading theory is that the missing baryons are hiding in the vast, diffuse regions of space between galaxies in the form of hot, ionized gas. This gas is so thin and spread out that it's incredibly difficult to detect with traditional telescopes. However, recent advancements in observational techniques have provided some clues. By studying the way light from distant quasars passes through these intergalactic regions, scientists have detected faint traces of this elusive gas. It's like finding invisible ink by shining a special light on it. Only in this case, the light is the radiation from quasars billions of light years away. Another possibility is that the missing baryons are tied up in the filaments of the cosmic web, the same vast network of dark matter and gas we discussed earlier. These filaments, which connect galaxies across the universe, could contain large amounts of hot gas that's too faint to see directly. Simulations suggest that this gas might account for a significant portion of the missing matter, but confirming its presence remains a challenge. There's also the intriguing idea that some of the missing baryons could be in the form of compact objects, such as rogue planets, brown dwarfs, or even small black holes scattered throughout the universe. These objects would be too dim to detect with current technology, but they could still contribute to the total amount of ordinary matter. The missing baryon problem isn't just a curiosity, it's a critical piece of the puzzle in understanding the universe's composition and evolution. Solving it could shed light on how galaxies form, how the cosmic web evolves, and even the nature of dark matter and dark energy. It's a reminder that, even in the vastness of space, there are still hidden corners waiting to be explored and mysteries waiting to be unraveled. As we continue to search for these missing pieces, we inch closer to a fuller picture of the cosmos and our place within it. Now turning to the 18th anomaly on our list, we encounter a chilling mystery in the cosmic microwave background, the CMB cold spot. This peculiar region, discovered in the early 2000s, stands out as an unusually cold patch in the otherwise uniform afterglow of the Big Bang. While the cosmic microwave background is remarkably consistent across the sky, this cold spot defies expectations, sparking intense debate among scientists about its origins and implications. The cosmic microwave background, or CMB, is the oldest light in the universe, a snapshot of the cosmos when it was just 380,000 years old. It reveals tiny fluctuations in temperature which correspond to the seeds of galaxies and galaxy clusters we see today. But the CMB cold spot is different. It's significantly colder than its surroundings, stretching across a vast region of space. At first glance, it might seem like a random anomaly, but its size and temperature deviation are so extreme that they challenge our understanding of the universe's early moments. One leading explanation is that the cold spot is the imprint of a supervoid, a vast, nearly empty region of space where matter is sparser than average. As light from the CMB passes through such a void, it loses energy, a phenomenon known as the integrated Sachs-Wolf effect. This could explain why the region appears colder. However, the size of the supervoid required to produce such a cold spot would be enormous, far larger than any void observed so far. Some scientists argue that the probability of such a void existing by chance is incredibly low, raising questions about this explanation. Another, more speculative theory suggests that the cold spot could be evidence of a collision with a parallel universe. According to this idea, our universe might be just one of many in a multiverse. If another universe collided with ours in the distant past, it could have left a distinct imprint on the CMB, such as the cold spot. While this idea is fascinating, it remains highly controversial and lacks direct evidence. Still, it highlights how anomalies like the CMB cold spot push scientists to consider possibilities beyond our current understanding of physics. There's also the possibility that the cold spot is simply a statistical fluke, a rare but natural variation in the CMB. After all, the universe is vast and even unlikely events can occur. However, the odds of such a large and cold region appearing by chance are estimated to be around 1 in 200, making it a significant outlier that demands further investigation. The CMB cold spot isn't just a curiosity, it's a window into the fundamental nature of the universe. Whether it's the result of a supervoid, a collision with another universe, or something entirely unexpected, solving this mystery could reshape our understanding of cosmology. It reminds us that even in the most well-studied aspects of the cosmos, there are still surprises waiting to be uncovered. As we continue to probe this enigmatic cold spot, we may find answers that challenge our deepest assumptions about reality itself. Now turning to the 19th anomaly on our list, we delve into the intriguing hypothesis of Planet 9, a mysterious, undiscovered world that may be lurking in the outer reaches of our solar system. While most of us grew up learning that our solar system has 8 planets, astronomers have been piecing together evidence that suggests there might be a 9th, hidden far beyond Neptune. This hypothetical planet, if it exists, could explain some of the strange gravitational patterns observed in the distant reaches of our cosmic neighborhood. The idea of Planet 9 first gained traction in 2015, when astronomers noticed that several small icy objects in the Kuiper belt, a region of the solar system beyond Neptune, were behaving in unexpected ways. These objects, known as trans-Neptunian objects, have orbits that are oddly clustered and tilted in a way that suggests they're being influenced by a massive, unseen force. The most plausible explanation is that a large planet, roughly 10 times the mass of Earth, is exerting its gravitational pull on these objects, shaping their paths over billions of years. But why haven't we seen Planet 9 yet? The answer lies in its distance. If it exists, this planet would orbit the Sun at an average distance of about 600 times farther than Earth, making it incredibly faint and difficult to detect. To put that into perspective, it would take Planet 9 between 10,000 and 20,000 years to complete a single orbit around the Sun. Its extreme distance and slow movement make it a challenge to spot, even with our most advanced telescopes. The search for Planet 9 has sparked a wave of excitement and speculation. Some scientists believe it could be a super-Earth, a type of planet larger than Earth but smaller than Neptune, while others suggest it might be a rogue planet captured by the Sun's gravity long ago. There's even the tantalizing possibility that it could be a primordial black hole, though this idea remains highly speculative. Whatever it is, the discovery of Planet 9 would be a monumental achievement, reshaping our understanding of the solar system's formation and evolution. The evidence for Planet 9 is compelling, but it's not yet conclusive. Astronomers continue to scan the skies using powerful telescopes and sophisticated computer models to narrow down its possible location. If found, it would be the first new planet discovered in our solar system since Neptune in 1846. Until then, the mystery of Planet 9 serves as a reminder that even in our own cosmic backyard, there are still secrets waiting to be uncovered. As we peer into the distant reaches of the solar system, we may find answers that challenge our understanding of the universe and our place within it. Now turning to the 20th anomaly on our list, we venture into the strange and elusive world of neutrinos, tiny, nearly massless particles that have puzzled scientists for decades. Neutrinos are among the most abundant particles in the universe, yet they are incredibly difficult to detect because they rarely interact with matter. Billions of them pass through your body every second, completely unnoticed. But what makes neutrinos truly fascinating is their unexpected behavior, which challenges our understanding of particle physics and the Standard Model. The mystery begins with something called neutrino oscillations. When neutrinos travel through space, they can change from one type to another, a phenomenon known as oscillation. There are three types or flavors of neutrinos: electron neutrinos, muon neutrinos, and tau neutrinos. Scientists initially believed that neutrinos were massless, but the discovery of oscillations proved otherwise. For neutrinos to oscillate, they must have mass, a revelation that shook the foundations of the Standard Model, which had long assumed neutrinos were massless. This anomaly was first observed in the late 1990s during experiments designed to study neutrinos produced by the Sun. Researchers found that the number of electron neutrinos arriving on Earth was far fewer than predicted. This discrepancy, known as the solar neutrino problem, was eventually explained by neutrino oscillations. The missing neutrinos hadn't disappeared, they had simply transformed into other types that were harder to detect. This discovery earned the scientists involved the Nobel Prize in Physics in 2015, but it also opened up a new set of questions. The implications of neutrino oscillations are profound. They suggest that the Standard Model, which has been the cornerstone of particle physics for decades, is incomplete. If neutrinos have mass, there must be new physics beyond the Standard Model to explain it. This has led to a flurry of research aimed at understanding the properties of neutrinos, including their exact masses and how they fit into the larger framework of the universe. Some theories even propose that neutrinos could be the key to understanding dark matter or the matter-antimatter asymmetry in the cosmos. Despite their elusiveness, scientists have made remarkable progress in studying neutrinos. Massive detectors, often buried deep underground to shield them from other particles, have been built to capture the rare interactions of neutrinos. Experiments like the Sudbury Neutrino Observatory in Canada and the Ice Cube Neutrino Observatory in Antarctica have provided crucial insights into their behavior. Yet, many questions remain unanswered. Why do neutrinos have such tiny masses? How do they fit into the grand scheme of particle physics? And what other secrets might they hold about the universe? The neutrino anomaly is a reminder that even the smallest particles can have the biggest impact on our understanding of reality. As we continue to probe the mysteries of these ghostly particles, we may uncover truths that reshape our view of the cosmos. With each new discovery, we move closer to unraveling the deeper mysteries of the universe, one neutrino at a time. Now turning to the 21st anomaly on our list, we encounter a cosmic puzzle that stretches across unimaginable distances, the mysterious alignment of quasars. Quasars, the brightest objects in the universe, are powered by supermassive black holes at the centers of galaxies. They emit staggering amounts of energy, making them visible even from billions of light years away. But what has left scientists baffled is the discovery that some quasars, separated by vast cosmic distances, appear to be aligned in a way that defies our understanding of the universe's structure. This strange alignment was first noticed when astronomers studied the rotation axes of quasars. Surprisingly, they found that the axes of these quasars, spread across billions of light years, seem to point in the same direction. This alignment is not random, it suggests a coordinated pattern on a scale so large that it challenges our current models of the universe. How can objects so far apart with no apparent connection exhibit such a synchronized orientation? The answer remains elusive, but the implications are profound. One theory proposes that this alignment could be evidence of a large-scale structure in the universe, far beyond what we currently understand. The cosmic web, a vast network of galaxies and dark matter, might play a role in shaping the orientation of quasars. Alternatively, some scientists suggest that this alignment could hint at the influence of primordial magnetic fields or other forces that operated in the early universe, leaving behind a cosmic fingerprint that we are only now beginning to detect. The quasar alignment anomaly also raises questions about the universe's evolution. If quasars are aligned over such vast distances, it could mean that the universe is not as random as we once thought. Instead, it might have a hidden order or structure that we are only beginning to uncover. This discovery has sparked a wave of research aimed at understanding the forces that could create such a pattern and what it tells us about the universe's origins and future. As we continue to study these enigmatic objects, the quasar alignment serves as a reminder that the universe is full of surprises. It challenges us to rethink our assumptions and pushes the boundaries of our knowledge. What other secrets might these distant beacons of light hold, and how might their alignment reshape our understanding of the cosmos? The answers to these questions could unlock new insights into the universe's grand design, revealing connections that span the vast expanse of space and time. Now turning to the 22nd anomaly on our list, we encounter a celestial masterpiece that stands out for its striking appearance, the Red Rectangle Nebula. Located about 2,300 light-years away in the constellation Monoceros, this nebula is one of the most visually unique objects in the night sky. Its name comes from its distinct rectangular shape and deep red hue, a combination that has fascinated astronomers and stargazers alike. The Red Rectangle Nebula is a protoplanetary nebula, a stage in the life cycle of a star that occurs just before it becomes a full-fledged planetary nebula. At its center lies a binary star system where two stars orbit each other in a cosmic dance. The interaction between these stars is believed to play a key role in shaping the nebula's unusual structure. As the stars shed their outer layers, the expelled material forms the nebula's intricate patterns, including the iconic rectangular shape and the ladder-like rungs that extend outward. One of the most intriguing features of the Red Rectangle Nebula is its vibrant red color. This hue is caused by a phenomenon known as photoluminescence, where ultraviolet light from the central stars excites hydrogen molecules in the nebula, causing them to emit red light. The nebula also contains complex organic molecules, including polycyclic aromatic hydrocarbons, which are thought to be building blocks for life. This has led scientists to speculate that the Red Rectangle Nebula could be a cosmic laboratory for studying the origins of life in the universe. Theories about the nebula's formation suggest that the binary star system's unique dynamics are responsible for its shape. As the stars orbit each other, they create a dense disk of dust and gas around them. This disk funnels material outward in two opposing cones, giving the nebula its rectangular appearance when viewed from Earth. The ladder-like rungs are thought to be shock waves caused by periodic ejections of material from the stars, adding to the nebula's complexity. The Red Rectangle Nebula challenges our understanding of how planetary nebulae form and evolve. Its unique structure and composition provide valuable insights into the processes that shape the cosmos. As we study this enigmatic object, it reminds us that even in the vastness of space, beauty and mystery are intertwined. What other secrets might the Red Rectangle Nebula hold? And how might its study deepen our understanding of the universe's intricate workings? The answers to these questions could shed light on the cosmic forces that shape the stars and the worlds they leave behind. Now turning to the 23rd anomaly on our list, we delve into a phenomenon that reveals the violent yet fascinating side of cosmic evolution, galactic cannibalism. This process, where larger galaxies like our Milky Way grow by consuming smaller ones, is a key mechanism in the life cycle of galaxies. It's a cosmic dance of destruction and creation, reshaping the universe on an unimaginable scale. Galactic cannibalism occurs when a larger galaxy's gravitational pull overwhelms a smaller neighboring galaxy, tearing it apart and absorbing its stars, gas, and dust. This process can take billions of years, but the evidence is written across the night sky. For example, the Milky Way is currently in the process of consuming several smaller galaxies, including the Sagittarius dwarf spheroidal galaxy. The remnants of these galactic feasts can be seen in the form of stellar streams, long trails of stars that trace the paths of the consumed galaxies. One of the most striking examples of galactic cannibalism is the Andromeda galaxy, our nearest galactic neighbor. Observations show that Andromeda has a history of devouring smaller galaxies, leaving behind a halo of stars and debris. In fact, astronomers predict that in about 4 billion years, the Milky Way and Andromeda will collide in a spectacular event, merging to form a new, larger galaxy. This collision will be a dramatic example of galactic cannibalism on a grand scale. The evidence for galactic cannibalism isn't just limited to visible remnants. Computer simulations of galaxy formation and evolution have shown that this process is essential for explaining the size and structure of many galaxies we observe today. Without galactic cannibalism, galaxies like the Milky Way wouldn't have grown to their current size or developed their intricate spiral arms. But galactic cannibalism isn't just about destruction, it's also about creation. The material absorbed from smaller galaxies can trigger new star formation, enriching the larger galaxy with fresh gas and dust. This process plays a crucial role in the ongoing evolution of the universe, shaping the galaxies we see today and those that will form in the future. As we study galactic cannibalism, we gain a deeper understanding of the dynamic and ever-changing nature of the cosmos. It's a reminder that even the largest structures in the universe are shaped by the forces of gravity and time. What other secrets might this process reveal about the history and future of galaxies? And how might it influence the fate of our own Milky Way? The answers to these questions could help us unravel the mysteries of galactic evolution and our place in the universe. Now turning to the 24th anomaly on our list, we explore a phenomenon that bends our understanding of time itself, time dilation in quasars. These incredibly bright and distant objects, powered by supermassive black holes, offer a unique window into the early universe. But what makes them even more fascinating is how they reveal the strange effects of time dilation, a consequence of the universe's expansion and the nature of light. Time dilation occurs because the universe is expanding, stretching the fabric of space and time as it grows. When we observe distant quasars, we're essentially looking back in time, seeing light that has traveled billions of years to reach us. But here's the twist: because the universe is expanding, the light from these quasars is stretched or redshifted, causing time to appear to slow down from our perspective. This means that events happening in these distant quasars seem to unfold more slowly than they actually do. For example, imagine watching a quasar's light flicker. From our vantage point, those flickers might appear to happen over thousands of years, even though they might have occurred in just a few days or weeks in the quasar's own frame of reference. This effect is a direct result of the immense distances and the expansion of space between us and the quasar. It's like watching a cosmic slow-motion replay where the passage of time is stretched to an almost unimaginable degree. This phenomenon isn't just a curiosity, it has profound implications for our understanding of the universe. Time dilation in quasars provides direct evidence for the expansion of the universe, supporting the Big Bang theory and our current model of cosmology. It also helps astronomers measure the rate of the universe's expansion, a key factor in determining the ultimate fate of the cosmos. Will the universe continue to expand forever, or will it eventually collapse back on itself? Observations of time dilation in quasars are helping us answer these questions. But time dilation doesn't just affect our view of distant quasars, it also challenges our understanding of time itself. In the realm of quasars, time becomes a relative concept, flowing differently depending on where you are in the universe. This idea echoes the principles of Einstein's theory of relativity, which tells us that time isn't a fixed, universal constant, but rather a flexible dimension that can stretch and warp under the influence of gravity and motion. As we study time dilation in quasars, we're reminded of just how strange and dynamic the universe can be. It's a place where time itself can bend and stretch, where the past and present are intertwined in the light we observe. What other secrets might these ancient beacons of light reveal about the nature of time and the universe, and how might they reshape our understanding of reality itself? The answers lie in the flickering light of quasars, waiting to be uncovered by the curious minds of astronomers and scientists. Now turning to the 25th and final anomaly on our list, we delve into one of the most mind-bending phenomena in the universe: quantum entanglement. This strange and seemingly magical behavior of particles has baffled scientists for decades, challenging our understanding of reality itself. At its core, quantum entanglement occurs when two or more particles become linked in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. It's as if these particles share an invisible connection that defies the limits of space and time. Imagine two entangled particles, let's call them particle A and particle B, separated by billions of light years. If you measure the spin or position of particle A, particle B will instantly reflect the same measurement, as if it somehow knows what happened to its partner. This instantaneous connection happens faster than the speed of light, which seems to violate the fundamental laws of physics as we know them. Albert Einstein famously called this spooky action at a distance, and even he struggled to accept its implications. But quantum entanglement isn't just a theoretical curiosity. It has real-world applications that could revolutionize technology. For instance, scientists are exploring the potential of quantum entanglement to create ultra-secure communication systems. By encoding information in entangled particles, it's possible to transmit data in a way that's virtually impossible to intercept or hack. This could lead to breakthroughs in fields like cybersecurity, where protecting sensitive information is critical. Beyond its practical uses, quantum entanglement also forces us to rethink our understanding of reality. It suggests that the universe is far more interconnected than we ever imagined, with particles sharing a hidden bond that transcends space and time. This challenges the classical view of a universe made up of separate, independent objects, and instead points to a deeper, more unified reality. Some scientists even speculate that entanglement could be a fundamental feature of the cosmos, woven into the very fabric of space itself. But perhaps the most profound implication of quantum entanglement is what it tells us about the nature of existence. If particles can be instantaneously connected across vast distances, does that mean the universe is fundamentally non-local? Could there be a deeper layer of reality where space and time are mere illusions? These are the kinds of questions that quantum entanglement raises, pushing the boundaries of both science and philosophy. As we wrap up our exploration of space anomalies, quantum entanglement stands as a fitting finale, a phenomenon that not only defies our current understanding, but also opens the door to entirely new ways of thinking about the universe. It's a reminder that the cosmos is full of mysteries waiting to be uncovered, and that the more we learn, the more we realize how much we still have to discover. What other secrets might the quantum realm hold, and how might they reshape our understanding of reality? The answers lie in the entangled particles of the universe, waiting to be unraveled by the curious minds of tomorrow. Now turning to the conclusion of our journey through these 25 space anomalies, it's clear that the universe is far stranger and more mysterious than we could have ever imagined. From the enigmatic wow signal to the mind-bending phenomenon of quantum entanglement, each anomaly challenges our understanding of reality in profound ways. These cosmic puzzles remind us that the universe is not just a collection of stars and planets, but a vast, interconnected web of mysteries waiting to be unraveled. These anomalies force us to question the very foundations of our knowledge. How can dark matter and dark energy make up most of the universe, yet remain invisible and undetectable? Why does the Fermi Paradox suggest that we might be alone in the cosmos, despite the overwhelming odds of extraterrestrial life? And what does the Great Attractor's gravitational pull tell us about the fate of our galaxy? Each question pushes the boundaries of science and philosophy, inviting us to rethink what we know about space, time, and existence itself. But perhaps the most exciting part of these anomalies is that they are not just unsolved mysteries, they are opportunities. They represent the cutting edge of human curiosity and exploration, urging us to dig deeper, think bigger, and dream bolder. Whether it's the search for Planet 9, the quest to understand fast radio bursts, or the exploration of quantum entanglement's potential, these anomalies remind us that the universe is full of surprises. So, what do you think? Which of these anomalies fascinates you the most? Do you believe that one day we'll uncover the secrets behind dark matter, or that we'll finally solve the mystery of the wow signal? Share your thoughts in the comments below. We'd love to hear your theories and ideas. And if you're as captivated by these cosmic mysteries as we are, don't forget to like this video, subscribe to our channel, and hit the notification bell so you never miss an update. The universe is vast, and the journey to understand it is just beginning. Let's keep exploring